For years, investigators, engineers, mathematicians, and independent analysts worked to understand what these satellite signals were trying to say. This graph represents one of the most important breakthroughs in the MH370 investigation. The Doppler behavior derived from Inmarsat burst frequency offsets. What made this graph so important was that it proved the aircraft was not simply stationary. It was moving relative to the satellite. And more importantly, the motion itself could be measured. Michael Exner and others helped demonstrate that the Doppler shift contained directional information hidden inside the signal structure. That changed everything. But even with this breakthrough, one major limitation remained. The signals were still primarily being treated as isolated measurements, points on a graph, corrections, frequency offsets. What you are about to see is the next stage beyond that. Instead of treating BTO and BFO separately, we begin treating them as a unified motion system, a live constraint environment, where timing, distance, direction, and continuity must all remain satisfied simultaneously. This is where the reconstruction stops behaving like disconnected points and starts behaving like motion. We start with BTO signals, not assumptions, not search zones, just signals. The first signal is the measured BTO error field. This graph represents the difference between the measured burst timing offset and the calculated satellite path timing between the aircraft and the ground Earth station. At first glance, it appears chaotic. Noise, random variation. But inside that apparent chaos is something important: continuity. The signal never completely loses structure. Even inside the error field, the aircraft remains constrained to a measurable timing relationship with the satellite system. The second signal is the distribution profile. The histogram shows us how the BTO error behaves statistically over time. What matters here is not perfection. What matters is containment. The signal errors remain centered around a measurable mean. That tells us the system itself remains stable enough to reconstruct motion from. The satellite system is not randomly drifting. It is operating inside a constrained timing environment. The third signal is the detailed breakdown. This is where we begin seeing the microstructure of the timing behavior itself. Short bursts, small oscillations, continuous corrections. The signal is constantly adjusting while still remaining inside a stable envelope. This becomes extremely important later, because once motion begins to organize, these same small timing structures begin revealing directional continuity. This is the foundation of the reconstruction, before headings, before turns, before flight paths. We begin with the raw timing environment itself, and once these signals are stabilized and constrained, we can begin combining them with Doppler behavior, motion continuity, and fixed anchor geometry. This is where the system begins transitioning from isolated measurements into live motion. Then we break the system down even further. Now we isolate only the BTO and BFO noise environment itself. No flight path yet, no assumptions about destination, no reconstructed trajectory, just signal behavior. We begin reducing the BTO noise field. The raw burst timing offset contains transmission variability, timing jitter, satellite timing uncertainty, and environmental noise. At first glance, the signal appears unstable, but once the non-essential variation is reduced, the underlying timing continuity begins to emerge. The important part is not removing the signal. The important part is revealing the stable structure underneath it. This is where the Doppler environment becomes visible. Raw BFO contains oscillator drift, satellite motion effects, aircraft motion effects, and system correction behavior. Once reduced, the directional continuity begins separating itself from the surrounding noise.